In this video, ladies and gentlemen, we're going to talk about different types of electromagnetic waves. Now, we've kind of gone through the whole electromagnetic spectrum, and we have looked at kind of the breadth of them, but I want to talk specifically about different wavelengths of light and where they're used. Now, most astronomy is done in the visible light spectrum. And remember our dear friend Roy G. Biv, and that each one of these wavelengths has its own unique color, and every color has its own unique wavelength. And this is very, very specific. And we're going to talk a lot about these different wavelengths of light. They can be used to help determine things like the motion of stars. The most famous space telescope is the Hubble Space Telescope. And the Hubble was launched back in the 1990s. And when Hubble was launched, it was specifically designed to look primarily at the visible part of the spectrum and a little bit into the infrared and a little bit into the ultraviolet. And it covers not only what you and I can see with our eyes, it also covers a little bit of the shorter ultraviolet wavelengths and a little bit of the longer infrared wavelengths. And Hubble was a game changer. It gave us information that astronomers did not have before due to its location above the Earth's atmosphere. Hubble is part of what is referred to as NASA's Great Observatories Project. And NASA's goal is to cover the whole electromagnetic spectrum, so that we can see everything from radio waves to gamma radiation coming from outer space. Now, Hubble, as I mentioned, is in the visible, plus some of the infrared and some of the ultraviolet. There are other space telescopes that have been put up, COBE, Spitzer, Chandra, that actually cover different portions of the spectrum. And we're going to talk a little bit about all of these. Now, light that is just a little bit longer wavelength than visible is infrared radiation. Infrared radiation is considered heat radiation. If there is a bonfire and there's a bunch of logs and there are flames leaping up and you're standing there holding your hands out next to the bonfire, you are going to get warm, not because you are touching the flames, heaven forbid you touch the flames, but you're going to get warm because there is heat that is irradiated or traveling through space towards your body. And those are infrared wavelengths of light. These are actually light waves. Every object emits some infrared radiation. Even objects as benign as carpeting sitting on your floor is going to emit some infrared radiation. We can tell an awful lot by looking at objects with infrared cameras. This is an infrared photograph of a home, and it's actually looking for heat loss. If you are a homeowner, a lot of power companies, energy companies like Northern States Power, Xcel, your rural electric co-op, they actually will send out a representative to take pictures of your home in the infrared and see where the energy is actually pouring out of your walls, and you can determine where you need to insulate. It's a pretty nifty deal and can save you long-term a lot of money. Human beings emit infrared radiation. And on this scale here, we see that the whiter and yellower colors are hotter. So this picture of this little boy, his neck is warm, his forehead is warm, the inside of his ear is warm. And of course, that's where parents take the temperature of children, across the forehead, in the inner ear. And I remember my mom, when I was little, she would like feel my neck, because those are the three places where the most heat is radiated from you. The cooler parts are, of course, hair, not so warm, and of course, tips of the ears and tips of the nose. This is a wonderful collection of pictures. I really love this. This infrared photography can be used by law enforcement officers. So here is a picture of a hallway taken in visible light, and here is a picture of a hallway taken in with an infrared camera. That infrared camera, can you see the footprints? Yeah, ain't that cool? So if you were looking for a perpetrator or a bad guy, there is no visible evidence that this person has gone that way, but they do leave a little bit of a heat signature, which is pretty nifty. In astronomy, infrared radiation can be used for a whole bunch of different things. Here is an infrared photograph of our star, our sun. And the places that are very, very dark, these are known as corona holes. The coronal holes are where lots of energy is pouring out of that star. And they are the hottest regions. Now you might go, but they're dark. Yeah, I know they're dark. But there are corona holes, meaning there's a lot of stuff being thrown out by the sun. This is a picture of the pinwheel galaxies, and the pinwheel galaxy under visible light and in infrared light. Now, what you can see under infrared is you can see all of these stars that are obscured by dust. I mentioned before that galaxies are full of dust, just like driving down a dusty dirt road. You can't see through the dust. Astronomers can't see through the dust. But if we look out in space with an infrared camera, we can see through that dust, and we can see the structure of the galaxy, this beautiful pinwheel structure, and we can see stars buried inside that galaxy. The Spitzer Space Telescope was launched in 2003 specifically designed to cover the infrared part of the spectrum. Now, the Spitzer Space Telescope is going to be replaced, and at the moment that I am recording this video, the James Webb Telescope has not yet launched. James Webb is due to launch sometime in 2018, fall of 2018. It may be delayed because that's the way it happens in science sometime. But this is going to replace Hubble Space Telescope and replace Spitzer. And it is specifically designed to cover the infrared part of the spectrum. And we'll talk more about James Webb later. Not all of the electromagnetic waves can reach the ground. Some visible light reaches the ground, some infrared reaches the ground, and we know that because our planet does get warm due to the sun. If infrared radiation did not reach the Earth's surface through its atmosphere, the Earth would not be warm. Some radio waves reach the ground, but a lot of the electromagnetic spectrum cannot reach the ground, and that's why we need space-based telescopes. These are some pictures of radio telescopes. This happens to be in Hawaii, a collection of radio telescopes up on a big mountain in Hawaii. This is Arecibo in Puerto Rico, a large radio telescope. And when we look out in space in the radio waves, we see things we don't normally see in visible light. This happens to be a quasar. A quasar is a quasi-stellar radio source. And these quasars, big, massive amounts of radio waves that are emitted by these quasars. Pretty nifty things. We have to have space-based telescopes for the ultraviolet, the X-ray, some of the infrared, and the gamma radiation. Why? Because our beautiful, fabulous Earth is surrounded by a blanket of air, and the air is like an insulating blanket. If you are lying in bed and you try and look through your blankets, you're not going to see an awful lot. And the same thing, when astronomers are on Earth and they're trying to look through the blanket of air, some things they can see and a lot of things they can't. And so we need these space-based telescopes in order to see beyond what we can see from the ground. One of the things that's really interesting, and we'll talk about these now and then through the semester, is balloons. Launching a satellite into space or a telescope into space is a big deal. It costs billions and billions of dollars. But they can actually, astronomers can actually put a telescope on the bottom of a big honkin' balloon. This balloon is larger across than a football field, and they can have this balloon orbit around above the Earth's atmosphere many days, weeks, months sometimes before it gets ruptures and falls. And they can do that much more cheaply than launching a space-based telescope. So balloons are actually used by astronomers. Kind of nifty. So we've talked about the radio waves. They can penetrate the Earth's atmosphere. We need telescopes for a lot of the infrared, microwaves, X-rays, gamma rays, and some, but not all of the ultraviolet. So let's talk about some of these higher energy, shorter wavelength, high frequency waves. There is a relationship between energy and frequency. Waves that have a high frequency have a high energy. So we're talking X-ray, we're talking gamma radiation. These are these high energy waves. Low frequency waves tend to have low energy. That is like radio waves. Low frequency, they don't oscillate very fast, they don't carry an awful lot of energy, and hence not terribly damaging or dangerous to people. But I do want you to know this relationship. High energy, high frequency. Low energy, low frequency. The L's go together, the H's go together. As we go past visible light, we go into the ultraviolet portion of the spectrum. Now, these are waves that are actually a little bit shorter in wavelength than visible light, and hence they are higher in energy. Now, these higher energy ultraviolet lights, these are the ones that give you a sunburn. These are the ones that when you're lying out, they're going to cause your melanin to make you brown. If you go to a tanning bed, that's ultraviolet, that's going to be emitted, and astronomers take pictures of stars and a lot of things in space using ultraviolet. X-ray, still shorter, much shorter wavelengths of light, and hence much higher energy. X-rays, as you know from going to the doctor and going to the dentist, can actually penetrate the soft tissue of your body. When you take an X-ray or get an X-ray taken, the bones and dense things in your body actually absorb the energy, and the flesh of your muscle and your skin allows the X-rays to pass through. And so when you physically look at an X-ray, it looks like a photographic negative, because this is where the white areas where the X-rays have been blocked, and the dark areas is where the X-rays have passed through. We've known about X-rays for 125, 130 years or so. They were discovered by a German fellow named Wilhelm Röntgen, and Röntgen actually discovered them by accident. And this is a picture of good old Wilhelm Röntgen. And the very first X-ray that he took of a human being was of his wife's hand. So he was messing around with this and he said, "Come here, honey." And this is a picture of Mrs. Röntgen's hand. And you can see she had quite a large ring on that hand. And that was the very first time human beings could peer into a human body without actually cutting it open. So it's been a wonderful gift to medicine, but it's also very important in astronomy. The Chandra X-ray Observatory is one of the NASA's Great Observatories project, specifically designed to look at X-rays. Now, where the heck are X-rays produced in space? Well, these X-rays are produced in high energy situations. Things like pulsars, quasars, and the event horizons of black holes. And we will talk about all of those in due time. But we can actually see some of the most violent and most energetic high energy events in space by looking in the X-ray portion of the spectrum. Now, we've looked at X-ray. The only thing that's left is gamma rays, so still higher energy. Gamma radiation is the highest form of electromagnetic waves, and it's produced by the most high energy types of events. Well, some of the most high energy types of events in space are the creation of black holes. And we now know that whenever a black hole is created, it emits something that is referred to as a gamma ray burst. And in order to detect these, NASA has launched the Fermi Gamma Ray Space Telescope. And the Gamma Ray Telescope, the Fermi Telescope, was launched in 2008, and it is there primarily to detect black holes and colliding galaxies. So very, very nifty stuff. Last slide in this section is this one. This happens to be the Whirlpool Galaxy, and to help you understand that each one of these wavelengths is useful to astronomers, This is one galaxy photographed in the radio, infrared, optical, ultraviolet, and X-ray portion of the spectrum. We use all of the wavelengths of electromagnetic waves because they each tell us something different. All right, that will end this ton, and then next time we're going to come back and talk about temperatures of stars. See you then.